Alright, so tonight this video is going to be about the moment generating function. And of course the moment generating function is very important in terms of being able to find things like the expected value, which again we call this the first moment. Now some things are very obvious why they are. Well, we've told you that it equals NP, for instance, for binomial. We've endeavored to show that a couple of different ways. So, you know, whatever, we'll get there on that guy. But this one here, the second moment, it's a big deal because that's obviously what the variance is. Variance is equal to the second moment. The second moment minus the square of the first moment. Okay? And then, of course, the third moment has to do with other things and so forth and so on. Okay? But it'd be really cool if we could find a function that will generate those for us. So all we have to do is just be able to just decide, hey, I want the first moment, the second moment, the third moment, whatever it happens to be. Okay? So what we're going to do is we're going to be given a function. So I'm going to start off with plus on. And so by definition, the moment generating function, the MGF, okay, it's going to be a function of t when we're done, is the expected value of e to the negative x t, or negative tx, I should write it as. Okay, and pardon me while I get my materials ready. I left my notes over here. I made a bunch of notes today. So, well, anywho, if I can find what page I put it on, that would be handy. Anyway, your book, I wrote this down so I wouldn't screw it up. Your book, so it's the expected value of e to the tx. It's actually e to the positive tx, my bad. And the reason for that has become obvious in a few minutes, okay? But the expected value, of course, is going to be the integral from negative infinity to infinity, okay, of e to the tx times my function. This function is my PDF, okay, dx, all right, if x is continuous, obviously. Now, we'll talk more about it, what happens if x is discrete. We'll do that in a few minutes. But let's do this one first, okay? And so what's going to happen with this is, well, if I have a discrete distribution, a continuous distribution, well, I need to know what my continuous distribution happens to be. So, for instance, suppose my PDF, or my f of x, if you will, was a exponential function with exponential, and that is, it looked something like this, e to the negative x over, let's just say beta for right now. Okay? Okay. And if that was my exponential function right there, oh, and then there's got to be a beta out front. There's 1 over beta out front, right? So that's my exponential function right there. Be aware that some books, not yours, but some books write them this way, where lambda is equal to 1 over beta. Okay. There is my exponential equation. So if I were to do this guy, remember exponential has to do with waiting times. It's the idea that x is bigger than or equal to 0, which means when we do our integral, it's going to go from 0 to infinity. And it's going to be e to the tx. I pull that 1 over beta out front because I can. E to the minus x over beta. Okay? Dx. Oops. Shoot. Come back. Come back. Now, first things first. Okay? Change that up a little bit. I'm going to rewrite these guys together. Okay? And I'm going to pull the x out of them. And so it's going to be e. And I'm trying to decide how I want to do it. I think I'm going to pull I'm going to pull a negative x out. Yes, I'm going to pull a negative x out, I believe. That's what I want to do. And that will leave me with 1 over beta minus t. I think you'll find, yes, dx. Okay? Now, if you antiderivative that thing, what are you going to get? Well, as you well know, you're going to have 1 over beta out front. Okay. When you antiderivative this thing here, well, this is a constant, and it's a -1 right there. So it's going to be 1 over that e to the minus x over that, right? Now, it's important that we integrate this baby from 0 to infinity. Okay, so what happens at infinity? Well, at infinity, of course, this is going to be e to the negative infinity, so it's going to be 0. So we're just wave our hands at that. It's going to be 0 on the top end, minus, if you put a 0 in for x, right? Well, you just get 0 for the numerator up here, correct? You just get 0 up here on top. So e to the 0 is 1, so you get this thing here. Now, this thing is a little weird looking, so I'm going to clean it up for you. And so this is our moment generating function. Make sure that I didn't drop a negative somewhere. Oh, yes, this should be a negative right here. There, we should have a negative right there, so this should be positive. Good for us. Okay? I just felt dirty. Now, you're like, well, this is 1 over beta, stupid. There we go. Cool. Now, what would be really cool is if I could rewrite this and make it a little prettier. So I'm going to do that, if you don't mind. Down here on the bottom, this is t over 1. So if you were to get a common denominator on the bottom, it would be 1 minus t times beta over beta, yes? And of course, that's going to be beta over 1 minus t times beta times 1 over beta. And so, in theory, if I didn't screw this up, these guys cancel out, and I should be left with this guy. 1 minus t times b. Okay. This right here should be my moment generating function, in theory. I'm going to pause while I check my notes. And this is actually correct. So a lot of books will rewrite this piece right here a little different than I did. So that would be lambda, that's 1 over beta, is equal to 1 over lambda minus t. That's a times right there, you idiot. So this would be lambda minus t. Okay, these two things are equivalent because remember lambda is 1 over beta. I don't really care which one you use. This one, I think the bottom one maybe is a little prettier to use, but I think I'm going to go this route. Maybe I might try this one too. Well, I'll try to do it both ways. So that is my moment generating function. Notice that the MGF is a function of t. So the game is this. If you take the first derivative, all right, evaluate at 0, you will get, in theory, the first moment. If you take the second derivative, evaluate at 0, you will get the second derivative, or the second moment rather, and so on and so on and so forth. Okay, I'm not sure which I want to do first. I guess we'll try it with this one just for a good time. So it's going to be 1 over 1 minus t beta, like so. If I were to take the derivative of this again with respect to t, well, remember this is the same thing as taking the derivative with respect to t of, and of course this is just 1 minus t beta to the -1 power, which would be -1 minus t times beta to the -2 times, now what's the derivative of this guy? Well, it's negative beta, correct? So the game is you're going to get negative beta over 1 minus t beta squared. Okay. In theory now, when I do this, I should get, in theory now, if I evaluate this at 0, I should get just beta. Okay. Now, if I did this correct, that one should be beta. The other one, if I do the other one up here, I should get 1 over lambda, and let's see if that isn't correct. If I take this guy here and integrate and derivate with respect, I'm going to rewrite it like this if you don't mind. With respect to t, Well, this is just a constant. This becomes lambda minus 1. If you take the derivative of this guy, oops, this is to the minus 1 power. This becomes negative. This becomes to the negative 2 times negative 1, correct? So it's going to become negative lambda, positive lambda rather, over lambda minus 2 squared, correct? And when t equals lambda, or t equals 0 rather, you're going to get lambda equal lambda, or lambda over lambda squared, which is 1 over lambda. 1 over lambda is beta. That works both ways, okay? So now you're like, well, that's cool, Jay. So wait, you're saying this is the second, that's the first derivative. This right here is the expected value of x. That's correct. So if I wanted the second derivative, I would literally just take this guy here and take a derivative again. That's right. Let me rewrite that for you. Okay? And so, of course, negative 2 lambda minus t to the minus 3 times negative 1, which would be 2 lambda over lambda minus t to the third. If you evaluate at t equals 0, you get 2 lambda over lambda cubed, which is 2 over lambda squared, which is, in fact, the variance. Oh, it's not the variance. That is, if you will, the second moment. It's e of x squared. Now, oftentimes, after all that work, and I believe you me, I've fallen victim to this many times. I went all this trouble, and I get this answer here, and then I go, look, and I say, hey, what's the variance? And I go, oh, the variance, that's not right, you dummy. But remember, you didn't solve for the variance. If you wanted variance, it would be this minus this. Correct? Well, this is 2 over lambda squared minus this guy squared, which is 1 over lambda squared. That is the variance for an exponential. And had you done it down here, what you would have found is you would have gotten beta squared. And so that's what you would have gotten for the variance. But let me just jump in right here. Let's look at this guy. So the second derivative here would be just beta. The first derivative would be 1 minus. Okay. Now if I take the second derivative, I'm going to get negative 2 beta. 1 minus t beta to the minus 3 times negative beta, yes? So that's going to just be 2 beta squared over 1 minus t beta cubed. You evaluate at 0, you're going to get 2 beta squared minus this guy squared is just beta squared. And that is another way of saying it. So that is for the exponential distribution. Okay? I'm going to go run. I'm going to go do a couple of the discrete ones first, and then I think we'll come back and take a look at some of those other ones here a little bit. Okay? So let's look at the actually. Yeah. So let's do that. So let's do binomial. Okay. So what is the expected value? I'm sorry. What is the moment generating function for a discrete, any discrete distribution? It's e to the tx, the expected value e to the tx. And what would that look like? Well, because it's discrete, where I goes from 1, well, maybe I should do n equals 0 to well, I do I goes from 1 to n. The idea being is that, for instance, if you're going to have n children, you can choose however many you want them to be girls, right? So anywhere from 0 to n of them can be girls. If you're flipping a coin 5 times, you get anywhere from 0 to 5 heads, for instance. Okay? So it's e to the tx times, now what is the PDF for a binomial? Well, we know it's n choose x, p to the x, q to the n minus x. True that? When you look at it, that makes sense? Well, the trick is always on this guy. Can I put this bit here with something over here that matches sort of the exponent? And the answer is right there. Yes, you can. So the game is, well, all right. This is going to be n choose x. That's p. Oh, let's don't do that. When I do these guys here, what do they have in common? Well, I can rewrite them as e to the tx. I'm going to write like this first. P to the x, like this, yes? And so, okay, that's great. And then q to the n minus x. Then in the next step, I'm going to go ahead and combine them a bit more. So it's n choose x. Now this is e to the t times p all to the x power. Okay? Actually, I think the way I like to write it better is p e to the t. But you do you. And then q to the n minus x. Okay? Well, if you think about that, what is that? Well, that's just a stupid binomial, right? That's just a dumb binomial kind of a thing. Where if you think about this, if you recall back in the day, and it may have been a long time since you've seen this, but you may remember or you may not remember, you can do binomial expansion using this guy right here. And if you don't recall what that's like, the way to do that is this. When you were like in somewhere in Algebra 2, maybe someone waved their hands at it one day and you're like, oh, that's neato. It's not really neato. So the game is you go, it's 3, choose 0, and then it would be, no, actually 3 choose 3. 3 choose 3, a to the 3, b to the 3 minus 3, plus 3 choose 2, a squared, b to the 3 minus 2, plus 3 choose 1, and then it's a to the 1, b to the 3 minus 1, plus 3 choose 0, and then it would be a to the 0, b to the third. Okay? The idea when I say that is this can be expanded to look like this. This could be rewritten as the sum, where I goes from 0 to n of n choose x of a to the x, b to the n minus x. Does that make sense? Because that's all we're saying. Because when you're up here, you're like, I don't really see where you're going with this, Jay. Bear with me. I am saying that back in the day, you learned that this guy right here could be expanded to look like this. Okay? And what I'm telling you is that this guy right here is another way of saying a plus b to the n power. Does that make sense? Okay? I hope so. Which means that my a up here is p e to the t. And my b up there is q to the n power. And so in theory, this should be my moment generating function. Notice that we got rid of the x's by doing that. That's kind of a big deal. They went away when we did the integral. They're going to go away right here as well. Now you're like, oh, wait, cool, but okay, I guess. How are you going to take the derivative of this thing, Jay? Well, remember, this is blah, blah, blah to the n power. If you take the derivative, that's going to become n times p e to the t plus q to the n minus 1, correct? Times the derivative of the inside, which would be p e to the t. Cool? That work for you? Okay, it's pretty exciting. Now check this out. All right, now this is all multiplied. Now let's evaluate such that t is equal to 0 now. Well, if you do that, this becomes n. This becomes p plus q to the n minus 1. You will make, a lot of us make a lot of mistakes on this part here because you don't see it. You're just like, oh, I didn't catch that. And then, of course, at t equals 0, this just becomes just p. What is p plus q? Remember, p plus q, this is probability of success, probability of failure, that's equal to 1. So this is simply np. This is the expected value of x. Okay? Now, if I want to take the second derivative and find the second moment, I'm going to take the derivative of this mess. Okay? And maybe you don't like it the way it's written, so I don't either. So I'm going to rewrite this as this, and then this. Okay? And it's at this juncture that I am not I'm not doing that by hand anymore. I don't get paid enough to do it by hand. Okay? I could do it by hand, but I don't feel a need to. You know, whatever. And again, doing it by hand, so Caleb, you're certainly welcome to do it by hand, sir. Okay? If you're doing it by hand, this is a product rule, so this is times this, and of course this is chain rule once again. Maybe I will do it by hand just for a good time. What is the derivative of this first part? It's just the first part, right? Because this is constant, e to the t, the derivative of e to the t is just e to the t, times the second function, plus the first times the derivative of the second function. Right? Okay, that's pretty cool. Now check this out. Okay, if you let this thing be evaluated at t equals 0, what ends up happening? Well, this becomes np. Again, this piece goes away, and you're left with p plus q is 1, plus stupid ear. Plus okay, this is going to be 1 as well. This is going to be p. Okay, we're good. We're good. Okay, that always freaks me out. I'm always like, no. Okay, so here's another p right here. Are you with me? So what I'm going to have, and this of course just goes away as well. So I'm going to have an n p squared times an n minus 1. Is that cool? This p times this p here, np squared, and then times n minus 1. This is the part that always fouls me up every time I do this, and it really gets to the point where you lose your confidence on some of these because you're just like, no, I know I screwed this thing up. np squared, it's n squared pn, there you go, minus np squared, and yes, right. Okay, okay, come on, Jay, you can do this. Let me pause one moment. I'm messing one small step up. No, it turns out I'm not wrong. I just had to think about it for a second. I'm not wrong. It just looks goofy. So I'm going to bring the n squared p squared over here, and then I'm going to combine these two guys for reasons that will become obvious in about a second. But remember, you're not solving for the variance. That always messes me up when I'm doing these problems because I always think to myself, oh no, I messed something up because I know what the variance is supposed to be. In fact, sometimes if you don't know what the variance is, you're better off because you don't screw yourself up. What have I just done? Well, I factored that out, so now I have np, and then what is the definition of 1 minus p? Well, p plus q is n, or 1 rather, so 1 minus p is equal to q. So I'm going to get n squared p squared plus npq. This is the second moment. Okay? So if I take this guy minus the first one squared, what you end up with is npq is the variance. Okay? So if you keep that in mind, that's what we're doing. This part right here is the expected value of x squared, the second moment, minus the first moment squared is the variance. And that's right. Now, as I was going to say, I was going to just do this for a good time. I'm going to come back over here to find my first moment generating function. It's that guy right there. Let's do this thing. So what I'm going to do is I'm going to just differentiate that, and I'm going to type it in as p, and I'm going to go ahead and use p. P times e to the t x, and you have to use t times x. Don't screw that up. Oh wait, I'm sorry, not p. Sorry, I'm sorry, I lost track of where I was. Just e to the t plus q to the n power, comma t. So there's my first. Oops. I closed my parentheses in the wrong place. I didn't add another one right there. Sorry about that. So there is my first derivative. Now watch me then evaluate that sucker at t equals 0. Nice. That's as far as it goes, and then you have to be smart enough to go, oh, yeah, that's right, p plus q is 1. Okay? Now, you're like, okay, well, that's great. Well, come back up here, and let's grab that guy again. Let's find the second derivative of it, yes? So, comma 2. So there's my moment generating function. And then, of course, I just grab it such that t equals 0, rather. There it is. And then, again, you have to be smart enough to know that p plus q is 1. And then, of course, you're still going to have to do some fancy footwork in here to get that to be n plus, to get that to factor out correctly. Okay. But what you end up with is, of course, this is 1, so you get np, and then it's np plus q in there, and then you can just do some fancy footwork there and make that come out right. Okay. It's pretty nice. I think you can even do this, but don't quote me on that. I think I can even do this, such that parentheses alpha p plus alpha q equal 1. Yeah, baby, look at that. Nice job, Jay. That kid. Not bad. Not bad. And so what you could do then here is I think I could put in a 1 minus p where the q is and get some stuff to cancel out nicely there. Is that what I want to do? No, it's n squared p. It's n squared p squared. No, that's actually what I wanted. N squared p squared plus npq. That's exactly what I want. Yay us. Okay. What you can do on this guy, if that bothers you, you can go to expand. There you go. Bam. Minus alpha n times alpha p squared. Bam, npq. Okay? So that's how you do the moment generating function for that guy. I'm going to pause for a second, get some more of my notes rejuggled around. We'll look at a couple more just for examples of them. Okay? Okay, the one for the normal is going to look like this. So again, it's the expected value of e to the tx, which of course is going to be the integral from, and of course we can go from negative infinity to infinity. That's not a problem. If you were doing this for like the heights of people, you just go from 0 to infinity because it doesn't make any difference. And then of course it's e to the tx times, and the PDF for a normal looks like this. Right. Okay, it's something along those lines. Okay. Keep in mind that all this gobbledygook here is a constant, so you can pull it out front. Okay. Yeah, I'm just going to go ahead and go from 0 to infinity because, again, this would be from, in the manufacturing world, it could be diameters, it could be weights, it could be a whole bunch of different things, so it's always going to be positive in that regard. That's not to say that that's not to say that you couldn't run into ones that weren't, but it's rare. Okay, by the way, don't forget it's x minus mu, the quantity squared up there. Okay, x minus mu, the quantity squared. All right, cool. So what I end up having now is e to the tx times e to the negative x minus mu squared over 2 sigma squared. Okay. Now, I want to put these in the same exponent, so what I can do, of course, is just do this, right? Right? Okay. And there's nothing wrong with that. It's just a little gross. So, and is it gross? Is it good? Is it iffy? Is it whatever? I'm not going to sit here and argue with you about it. I think what I might want to do, though, is to realize that when it's this situation up here, that e to the 2 sigma squared in the bottom there, 1 over 2 sigma squared, that bit there is just a constant. So when I take the derivative with respect to x, And when I take the integral with respect to x, that part doesn't change per se. It's not going to be all weird on us or anything. So what I think I want to do is 1 over 2 pi sigma squared, 0 to infinity, e to the, okay, now if I FOIL this mess out, that's going to give me negative x squared plus 2x mu minus mu, it's going to be minus mu squared plus, and then I'm going to get a common denominator, so it's going to be 2t sigma squared x all over this denominator. Does that make sense? Now, better, worse, different, I don't know what it is. Okay? But let's think about that for a second. So, what one might have should have done here in a second, I think I'm going to simplify it just a second here. What one might have done maybe is do some substitution, but we'll talk about it in a second. So at this point you're like, geez, what a god-awful mess. And you're not wrong, friend. You're not wrong. So what if we said, hey, let's let u equal what? Well, it'd be really cool if I could just make this e to the negative 1/2 u squared. That'd be really cool if I could pull that off. Well, what would that mean then? That means my u would be x minus mu over sigma. Does that make sense to you? Because if I let u be this whole, that whole thing, shoot, you idiot. Go back. There you go, stupid. If I let u be that whole thing, x minus mu over sigma, and if I make this substitution before I go any further, what's going to end up happening is equal to that u is equal to that. Then du would be equal to, well, it'd be 1 over sigma dx, yes? Which means that sigma du is equal to dx. Now what that does then is it changes this complexion of this thing up here. So let's come over and take a peek at that. A couple things pop up in my mind. First of all, I'm going to have this bit out front is still the same. Okay, I'm going to put that sigma out front now. Okay, 0 to infinity. I've got this e to the tx here. But here's where it gets fun now. Now it's going to be e to the minus x, not x squared, u squared over 2. Okay? Minus u squared over 2 in that regard. Okay? Now, think about that for a second. Does that feel okay to you? Maybe, sort of, kind of, ish? Okay? Sort of, ish? Kind of good? Okay, so I hope so. So then what is that going to do for us? Well, wait a minute now. I have this freaking x floating around. How in the devil am I going to... I can't have an x and a u in the same thing. Well, first of all, let's check this out. This guy and this guy are going to cancel off, yes? So I need to do a substitution. Well, if u is equal to this, that means that x is equal to u sigma plus mu. Is that true? Okay. And so what I end up with is 1 over 2 pi, which is absolutely correct. So now I have e to the t times it's u sigma plus mu, right? And then times, so we're going to be adding this guy here, right? Everybody got that? Okay. So now we're going to be integrating with respect to u. Okay, well, how does that work? Is there a way I can monkey with that? Well, yes, there is, and I'm going to get there in a second and show you that. Now, we're going to be integrating with respect to u. So what would happen if I pulled that out and did some different things with it? That's what the whole key point of this is going to be in a second. Okay, this thing is just always messy, and don't panic if it makes you look bad, because it makes the rest of us look bad too. Okay, don't panic. It's the square root of 2 pi out there. Now, here's what happens here. I'm going to go ahead and put the negative infinity back on here. For reasons it'll become obvious in just 1 second. I should never have gotten rid of it. In my mind, I was thinking one thing, and then I forgot where I was going. And I apologize up front once again for you perfectionists. Next term, if you'd had me next term, I'd be a little more on the ball. Second time teaching this class, have all my stuff in front of me, feel good about myself. You know that whole bit. Now, I'm going to go ahead and distribute this. So this really becomes, and for a reason, it'll become really obvious as soon as you see it. As soon as you see it, you're like, oh, well, duh. What I'm going to end up with is, this is going to be e to the mu t, right? Plus, not plus, times e to the t u sigma, and then times e to the minus u squared over 2 du. Right? Right. Excellent. Excellent. All right, so then the question then is simply this then, okay? When I do this integral, okay, what am I going to get when I do this integral here? So this first part here can come out front because it has nothing to do with du. You see this? So that's going to be out front. 1 over 2 pi square rooted. Yes? Now, what do I have inside? Well, inside I've got this thing here and this thing here, which is e to the tu sigma, okay, times e to the minus u squared over 2 du, okay? Yeah, I thought all was lost, but I think I did. I think I caught myself. I was like, where did I go wrong on my notes? I think I got it figured out what I did wrong. All right, I think. Now, I'm going to go ahead and rewrite these guys back up in the numerator of the, back up in the doohoo there. So it's minus, and this is u squared over 2. And then, of course, I want this stuff here to be over 2. So I'm going to go plus 2. And then I think I'm going to write it as t sigma times u, if that's okay with you. And while I'm at it, I'm going to pull that negative out and write it like this instead, if that's okay. And so what I'm going to do is I'm going to complete the square, which is just gross. It's just sick, and I'm so sorry, but we have to do it. So what's going to happen is this. When I complete the square up here, I need to have half of this middle dude squared. So half of that's going to be t sigma u, the whole shebang squared. That make sense? The whole shebang squared. Okay? And, oh, I'm sorry, not the u. Sorry. T squared sigma squared. There we go. Got it. Okay? Now, remember, what does that give us? That gives us that this is u minus t sigma squared. That's what it gives us. Okay? That's the whole point of doing that. Okay? So what have I added? I've added, quote unquote, I've added this guy over 2, right? So I've added t squared sigma squared over 2. But really it was negative, right? And really it wasn't added at all. I really said it was e to the negative of that power, which means I need to multiply by e to the positive of that power, sigma squared, over 2, in order to not have a problem with it. Does that make sense? It has to be there. Otherwise, I'm going to have an issue with it. Okay, now, let me do some rearranging again. I'm going to bring this out front. And then when I bring it out front, when I bring this bit out front out there as well, I realize, well, they have the same base, so that I can just rewrite this as, and I'm going to write it as 1/2 t squared sigma squared, if that's okay with you. Okay? And then what I'm going to do is I'm going to run this 1/2 pi routine back inside for reasons that I hope are quite obvious momentarily. And I'm going to rewrite this as e to the minus u minus t sigma squared over 2. Okay. Well, wait a minute now. That's interesting, I guess. And some people at this point are going, well, why did you go to all that rigmarole? Couldn't you do that easier? You'll see. Now, at this point right here, if a person were to think about this, what is u? We said u is equal to what? We said it was equal to x minus mu over sigma, right? If a person were to stick that back in and complete the square and all that rigmarole, you can see where you'd end up. But here's the issue. When I pulled that out, I didn't change the actual function, right? And I took care of the Jacobian. Everything is cool. So what should this bit right here integrate to? Because it's still a PDF. So it really should integrate to what? 1. So my moment generating function is simply this thing right here. Oops. Geez, it took long enough to get to that, and I'm so sorry. Okay? That right there is my MGF for the normal distribution. That's for any normal distribution. Okay? Now, I happen to like this one. I happen to like the MGF as a function of t, but it for any mu and any sigma. Yes? But what if my mu was 0? That is, what if it was the standard normal? If it was the standard normal, that is, normal 0, 1, if that were true, then this moment generating function then would become e to the t squared over 2. T squared over 2. And yeah, that should be it. E to the t squared over 2. Exactly. That's exactly what it would be if it's the standard normal. So this is all normals. This is normal mu sigma. Okay, and this is the standard normal. Okay, now, I happen to think that this one's kind of a big deal. Okay, let's take the derivative of this thing with respect to t one time. Let's see what happens. So I'm going to get, obviously, e to the mu t plus 1/2 t squared sigma squared times the derivative of this mess, which is mu plus, that's going to be t sigma squared, correct? Now, evaluate that when t equals a goose egg. Well, this is e to the 0, which is 1. This is, this is 0 times sigma squared, which is 0, so it's just mu. That is, the expected value of a normal distribution is mu. Well, I'm shocked. I'm not shocked. Now, again, sometimes getting here is a giant pain in the buttocks, but once you get to the moment generating function, oh my gosh, it's so awesome. And so what that means is every single one of these moment generating every single function that we've looked at, gamma, exponential, binomial, Poisson, all of them have known moment generating functions. Every single one of them. Okay? And so when you run through them, you're like, well, I want to use that moment generating function to find the third moment or the fourth moment or whatever it happens to be. Okay? If that's what I want to know. Well, okay, well, that's kind of neat. Well, then I just found it. There it is. And I can just pick whichever one I want. So now I need the second derivative. So now it's a product rule. So the derivative of this first part is the whole thing. We just did that. So I'm just going to rewrite that. And then plus the first, times, I'm sorry. That's the derivative of the first times the second plus the first times the derivative of the second with respect to t, so it would just be sigma squared. Does it make sense? Okay, this is the expected value of x squared. Now let's evaluate it at 0, so this just becomes 1. When t is 0, this is mu. This is also mu. When t is 0, this is 1, and this is sigma squared. So it's mu squared plus sigma squared. You can already see where this is going, can't you? Hey, what's the variance, Jay? Ooh, the variance is the expected value of x squared minus the expected value of x squared. So that would be mu squared plus sigma squared minus mu squared, which is just sigma squared. That's pretty awesome. Okay? So yeah, so just be it, that's how those work, okay? Now, can I use the moment generating function, you know, to do a variety of other things? Yes. And so that's kind of how these games work here. So I'm going to do an example one here in a second to kind of see what you think about it. I'm going to get my notes situated here. Okay. So hypothetically, if you had a binomial distribution, and if you don't recall, let's go back and look that up. Binomial was right here, p e to the t plus q to the n. Okay. So if this were true if this were the moment generating function for one of my variables, like say for column A, and I had another one in this column for column B, okay, and so it's a different, let's say P1 and Q1, P2 and Q2 to the N. And if column C were A plus B or something of this nature, okay, what would the expected value of these guys be? It's a good question. So suppose, again, completely hypothetically here, when we do these problems here, how would we find the moment for this guy over here? Well, if we're going to find the moment for this guy, we would simply take, turns out, and because these are independent events, you take the moment generating function for this first guy, and you multiply it times the moment generating function for the second one. Okay, and so this becomes the moment generating function for x plus y. Okay, that's how it works. So it's kind of nice to know that it works that way. And so when you do that, okay, then you could actually, you go through and check yourself out. Okay, and so if this makes sense to you, all right, let's try this here. Well, what would the derivatives be with respect to t? Well, it'd be a product rule this time. So it'd be n times p1 e to the t plus q to the n minus 1 times p1 times p2 e to the t plus q, there's a p there somewhere, q2 to the n plus the first times the derivative of the second okay, and now if you look at this, if you evaluate when t is equal to 0, you end up with n times, this is p plus q, and any p plus q just cancels out, so that's handy. So that's just 1 times p1 times, now times p2, okay, and then of course when t is equal to 0, this all becomes 1 plus, and then this bit right here is going to be what? Well, it's going to be 1. It's going to be 1 times n times 1 oh, there's what happened. That P2 is not supposed to be there. That was freaking me out. Whew. There we go. Ha ha! Good. Good. Huzzah! Anyway, so there you go. So it becomes np1 plus np2. That is p1 plus p2 times n. Okay, their means are added together. Okay? If you did the second moment, what would happen? Well, I don't know, but I could probably do it. So the second derivative would be the derivative of these guys here, which is just gross. It's gross. The things I do for you people, I swear. You know, jeez. What a great guy. I mean, really. Holy buckets. I'm just going to rewrite it because I can't do it the way it was written because it's just sick. If this works, I'm going to be pretty darn happy with myself. I have to actually celebrate or something. No, don't be ridiculous. I don't know what I mean celebrating. I get to have a... Oh, for gosh sakes. I don't know, get to go to bed earlier than normal. Alright, so it's product rule again, but it's the derivatives with respect to t. Notice that there is no t here. None. So it's just a constant, so it just tags along for fun. So then times n minus 1 times p1 e to the t plus q1 n minus 2 times p1 times this guy right, good, plus now I gotta do it the other way around for this fella. So then it's again the np1 doesn't change, the first one doesn't change, and then times n p2 e to the t plus q2 n minus 1 times p2. Good grief. Plus, that's a constant again, so np2, and then it's going to be n times p1. Oh, and by the way, all these first n's should have been n1s and n2s, but we'll get to that. You can kind of see how it's going to all shake out in a minute. I promise we'll get there when it's all done. Okay. P1 e to the t plus q1 the n minus 1 times p1 plus, times p2 e to the t plus q 2 n minus 1 plus np2, the first one, times n minus 1 p2 e to the t plus q2 n minus 2 p2. What a gross mess. Okay, so this should be n1 p1 n1 minus 1. This is going to cancel out to 1. This is also going to cancel out to 1. And they're getting the p1 floating around, so it's going to be that guy. Okay? Plus, here, this is n1 p1. This is 1. This should be an n2. n2 p2 plus, this is n p2, and this guy right here should actually be an n1 and an n, no fart, no fiddle farts. Yeah, this should have been n2 right there. So this should have been n2, and then we get another n1 and a p1, and this is a p2. That's cool. And then plus, and then the last piece, because these of course are all ones. And so you get an n1 n2 p2 squared. I think that should be pretty good. So it should be, now let's distribute this mess out like we did last time. That's n1 squared p1 squared minus n1 p1 squared plus n1 p. There's two of those guys in the middle, right? Plus, there's an n minus 1 here as well. And n2 squared p2 squared minus n2 p2 squared. Whew! Doggies. Now, this is your second moment, right? So if I take that and I subtract from it this guy, squared, I should get variance, the variance of the sum. So it's going to be n1 p1 squared minus, I'm going to leave it like this, I think, just for fun. We'll see if I like it in a minute. Plus, I got two of them. Plus n2 p2 squared minus n2 p2 squared minus, and if you FOIL that out, you're going to get n1 p1 squared, right? Minus 2 n1 n2 p1 p2 minus n2 squared p2 squared. Bam! Cancel, 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 cancel. Something's not quite kosher. Oh, you click. What'd you do? You crossed out the wrong thing, stupid. Okay. Well, one moment, please, while I figure out what I screwed up again. Alright, so I'm not finding out where I made my mistake, so I'm just not going to play with it anymore. So what I'm going to do is I'm going to take the derivative on the calculator. You notice I let P and Q be P and Q. That's P and Q1. And then I'm going to let X be my N1 and Y be my N2 and M and N be my other P and Q. I can't do anything better than that on the calculator. Obviously, all I'm doing wrong is I'm going to hold my mouth right somewhere along the line. Okay, there's that. So then I'm just going to say, all right, let's grab that guy. Grab it such that t equals 0. Okay. And then I'm going to also run through there and say, all right, so grab this guy and then say such that parentheses p plus q equal 1. There's that. And I can do the same thing with the M and the N. Okay. So I'll grab it again, such that, and there's another fancy way to do that as well, but it's not a big deal to me that you know how to do that. It's a little over the top fancy, I think, but you do you. So then we end up having N1 P1 plus N2 P2, okay, which I don't think is shocking to anybody. That's what I got the first time. So that wasn't why I used that. Well, the reason I used it is because obviously my derivative was wrong on the second one. My derivative, or somehow my solving went wrong. So here's my second derivative. It's obviously gross. It's why it's taking a long time. Funny, I could do it faster by hand. Oh, wait. Yeah, I think I screwed it up too, so I don't know. So here's the, come on, Betsy. You can do it. Come on. So I'm going to do it this way, comma, t. I'm just going to do the first derivative of the first derivative, which is the same thing, but I think it may find it easier if you, like, it's already bitten off part of its, it's already bitten off part of it, in other words. I already did the first derivative, so now all I have to do the second derivative. We'll play it by ear and see what it does. It's one of those deals where it's interesting. Sometimes a person can actually do it faster by hand. I know, Caleb, once in a while it's true. For heaven's sakes. For heaven's sakes. Oh, that's gross. Now, I'm just going to grab it such that t equals 0. Come on, it doesn't take this long. Just throw 0 everywhere there's a t. Attaboy. Good. Now clear that. Clear. Grab that again. Go such that parentheses p plus q. Q, I say, equals 1. I'm gonna be really angry if I don't do any better than I did by hand. Alpha m plus n equal 1. So I'm left with this mess here. Okay? Now, what I'm going to do is I'm going to grab that guy minus parentheses. I'm going to go find where I have my expected value of x. Just the expected values is this guy here. So I'm going to subtract that thing squared and end up with this mess here. Yes. And interestingly enough, I don't want to. Interestingly enough, I'd like to see if I could simplify that a little bit. Okay. So you're like, well, okay. Does that make it any better? Does that make it worse? What's going on here? Okay, and that is actually a correct statement right there. And the reason for that is because, remember, this is a variance issue. Let's see here. There's a covariance piece going on with that guy right there too. So part of that we would just assume to be 0. Of course, I got to figure out which part of that to do. All right, one moment, please. All right, so I'm punting on that, finishing it off there. This is actually the correct nasty thing up here, wherever that was, up here. That was actually the correct formula, and for whatever reason, it won't drop out nicely like it's supposed to. What it should have dropped out to was N1 P1 Q1 plus N2 P2 Q2. Now, for the life of me, I can't see how to factor that. I'll see if I can get that fixed and send out a little blurb with it. But what I did was I just chose P and Q and N to be specific values. I evaluated that function. I got 5. I evaluated the other function. For whatever reason, I chose x, m, and n. Oh, this is x, rather. This is y, m, and n to be these values. And they came out to be 3.2. Came out to be 8.2, which is exactly what it was supposed to do. Okay, exactly what it was supposed to do. Okay, so I feel pretty good about that. Moment generating functions, again, once you found them, simply take the derivative with respect to t, evaluate it 0. That's your first moment. Take the second derivative, evaluate it 0. That's your second moment, and so on and so on and so on. Okay?